Hey everyone, today we're going to learn how to solve a real-world problem using rational equations. Now these real-world scenarios can often be modeled with rational expressions, especially those that have to do with time and distance. Now distance is equal to the rate at which you are traveling times time. So therefore, if I'm going to solve for time, we would divide the rate to both sides and get that time is equal to distance divided by the rate, where rate is just another word that we use for speed. Now the reason that we're using time is because a lot of the times these word problems are going to tell you something about the time that it takes to travel somewhere. So we're going to write the equations in terms of time. So let's start off with this word problem and see if we can break it down. Kelsey is kayaking on a river. She travels 5 miles upstream and 5 miles downstream, in a total of 6 hours. In still water, Kelsey can travel at an average speed of 3 miles per hour. What is the average speed of the river's current? So, first of all, upstream and downstream. Let me explain the difference. Upstream is when you are traveling against the current. Now the current is basically what the water is doing. So like think about when we go to the beach. When you're about to go into the water, the current is going towards you because the water, like the waves are going towards you as you're trying to get in. So when you're going into the water, those waves are going against your movement, so it slows you down. Now when you're trying to get out of the water, you're going with the current. So because the waves are going in the same direction as you are, so those waves are going to increase your speed. And so you're going to come out of the water faster. So if you're ever told something where you're going upstream, you're going against the current. Downstream, you're going with the current. So again, against the current means you're going to slow down. With the current, you're going to speed up. And it all depends on what the actual speed of the current is. So in order for me to write an equation, notice that they tell you how long her trip took. That means that the time it takes to travel upstream for Kelsey plus the time it takes to travel downstream is going to equal to the total time of her entire trip. So this is like a verbal description of the equation that I'm going to write. So we're just going to focus on how to write the equation. Then we'll look at how to solve it. So let's see if we can break this down even more. I have created a chart here where we can write out what the distance and the speed, which is the rate, and then how to write the time. Let's start with Kelsey going upstream. It says that she travels 5 miles upstream. So that's her distance, which is 5. Her speed, it says here that Kelsey can travel at an average speed of 3 miles per hour, but she's going upstream. So she's going to slow down because of the current. So she's going at 3 miles per hour minus x, where x is going to represent the speed of the river's current. So it's how fast she's traveling minus the current because she's going against it. It's going to slow her down. And that time in total, right, remember that time represents distance over rate, would be 5 over 3 minus x, the distance over the rate. Going downstream, it says that she's also traveling 5 miles downstream, but her speed is now going to be faster because the current is going to push her. So it's the 3 miles per hour that she's traveling plus the speed of the current. Since again, upstream, the current is going to push her, so it's going to make her go faster. So the time for her to go downstream is going to be the distance over her rate, which is 3 plus x. So now I'm going to come back here to my verbal description so I can write out the equation that I'm going to use. We have the time that it takes for her to travel upstream. This is the time, 5 over 3 minus x, plus the time that it takes for her to travel downstream, which is 5 over 3 plus x, and that's going to equal to the total time. In the problem, they tell you that it takes her a total of 6 hours. So it's going to equal to 6. So this is the equation that I'm going to use to solve for the speed of the current, since that is what x represents. So let's look at how to solve that. This was again the question or the problem that we're working on. 5 over 3 minus x plus 5 over 3 plus x is going to equal to 6. We know how to solve this. This was the previous lesson that we did. We have to look at what the LCD is. The LCD, if I look at my denominators, 6 is just over 1. My denominators would be 3 minus x and 3 plus x. My excluded values would be x cannot equal to 3 nor negative 3, since that's when those denominators would equal to 0. So now remember, this is a rational equation that is being added, so I have to take the entire rational equation and multiply it by the LCD. So I'm going to do 3 minus x times 3 plus x times my entire equation. So now we distribute. When I distribute the LCD to 5 over 3 minus x, those 3 minus x's would cancel. So the only thing that I would multiply is this 3 plus x with the 5. Moving on to the next rational expression here, when I distribute it, the 3 plus x in this denominator would cancel with the 3 plus x with the LCD, so the only thing that I would multiply is the 3 minus x with the 5. And that's going to equal to, now when I distribute the LCD to the 6, nothing would end up canceling, so I have to multiply 6 with 3 minus x with 3 plus x. So now we have to distribute everything. So I'm going to distribute this 5 and this 5. And then before I distribute the 6, I'm going to distribute these binomials. So what this would give me is 15 plus x. Plus 5x. Plus 15 minus 5x. And that's going to equal to 6 times, now I'm distributing these binomials, so 9 plus 3x minus 3x minus x squared. Let's combine like terms. Here we have 15 plus 15, which is 30, and these 5x's would cancel. And that's going to equal to 6 times 9, these 3x's would cancel, minus x squared. Now, although this is a quadratic, what we see here is that we have x squared by itself, basically. We only have one variable, so I can just solve for this variable. Now, I can start off here by dividing the 6. You can either distribute the 6 and then solve for x, or since this x is being multiplied, I can just divide it to keep my number small. So 30 divided by 6 is 5, and that's going to equal to 9 minus x squared. Subtract the 9, we get that negative 4 is equal to negative x squared, and then divide the negative 1 to get rid of that negative. So we get x squared is equal to 4, square root both sides, and we get that x is equal to plus or minus 2. Now for all of these word problems, there's only one real solution. X, remember, represents the speed of the current. Speed cannot be negative, so I can just discount the negative answer. And 2 is not one of my excluded values. Therefore, the speed of the current is 2, and then our units is miles per hour, since that what was given in the problem. If we look back here, all of the units were miles, miles, and miles per hour. So we want to stick to the same units. So that would be the speed of the current. Let's look at another example. We have here that Chuck and Dana agreed to meet in Chicago for the weekend. Chuck travels 104 miles in the same time that Dana travels 96 miles. If Chuck's rate of travel is 4 miles per hour more than Dana's, at what speed does Chuck travel? So first of all, let's define our variable. We're trying to solve for here what's Chuck's speed. So that's what x is going to equal to. Just so that we can keep that in mind. Now it says here, what does the word problem say about the time it takes Chuck and Dana to travel? And how can we express this as a verbal equation? It says here that Chuck and Dana, that Chuck travels 104 miles in the same time. So that means that Chuck's time is going to equal to Dana's time. Now we have to write an expression that represents Chuck's time and an expression that represents Dana's time. Remember that time is equal to distance over the rate or speed. So Chuck's time. Chuck is traveling 104 miles. So that's his distance. Over. Now Chuck's speed, that's x. So I'm just going to use x. Now let's do Dana's time. Dana's time is her distance. It says that it's 96, so distance, over her rate. Now it says here that Chuck's rate of travel is 4 more miles per hour than Dana's. So that means that Dana's time is Chuck's time, but minus 4, since Chuck travels 4 miles per hour more. Now, it's ready to actually solve. So we have this verbal equation here. So I'm just going to replace Chuck's time with Dana's time. Chuck's time with this expression and Dana's time with this expression. So we have 104 over x is going to equal to 96 over x minus 4. Since there is no adding or subtracting, we can just cross multiply. And what we get here is 104 times x minus 4 is going to equal to 96 times x, or 96x. Distribute the 104, and we get 104x minus 416. And that's going to equal to 96x. Now our goal here is to solve for Chuck's speed, which is x. So I'm going to isolate the x. I'm going to subtract this 104 over to the other side, so that way I have combined my x's, and I get that negative 416, negative 416 is going to equal to negative 8x. Divide by negative 8, and we get that x is equal to 52. So this is Chuck's speed. So remember our units, everything here was given in miles per hour. So this is miles per hour. Let's look at one more. Here we are told that a plane flies 450 miles with the wind and 300 miles against the wind in the same length of time. So same length. If the speed of the wind is 29 miles per hour, what is the speed of the plane in still air? So that's going to be my variable. X is going to be speed of the plane. Now, how can I write out an equation that would represent this scenario? So remember that time is equal to distance over rate or speed. In this case, we have here that a plane flying with the wind for 450 miles flies in the same time as it's flying against the wind. That is my verbal equation. So now I need an expression that represents with the wind and an expression that represents against the wind. So let's start with the wind. Now this kind of a question is the same thing as with the current and against the current. The wind acts like the current. The wind can either speed up the plane or it can slow down the plane depending on how fast the wind is traveling. So we have here that the distance that the plane is flying with the wind is 450 over the rate. So the rate of the plane, that's what I don't know. I don't know the speed of the plane. So that would be x, but the wind is going to push it, so it's going to be faster. So we're going to add the speed of the wind, which is the 29. Now for against the wind, it is traveling for 300 miles. I am looking for the speed now down here of the plane against the wind, and that would be x, the speed of the plane, minus the speed of the wind, because the wind is going to slow it down since it's going against it. So now that I have these expressions, this is my verbal equation here, so I'm going to make this rational expression equal to this one. So 450 over x plus 29 is going to equal to 300 over x minus 29. Now we cross multiply. Since here there is no addition problem or subtraction, so we don't need to use the LCD. So this is going to give me 450 times x minus 29. And that's going to equal to 300 times x plus 29. Distribute the 450, and we get 450x minus 450 times 29 is 13,050. And that's going to equal to 300 times x, which is 300x, plus 300 times 29, which is 8,700. So now this is not a quadratic equation, so I can just isolate the x. So I'm going to move my x to the left, and I'm going to move these numbers to the right. So I'm going to subtract this 300x so that my x's are all together. And I'm going to add this 13,050 over to the other side as well. And we get here 150x is going to equal to 21,750. Our last step would be to divide by 150. And we get that x is equal to 145. And our units here would be miles per hour. So that would be the speed of your plane. So now you'll notice in this example, we had in the rational expressions in the denominator x plus 29. But in this rational expression that we did before, we had, not that one, we had 3 minus x. So the x changed positions, and it all depends on what you're solving for. So as a guideline for the denominators, when you're talking about rates, it's always the speed of the vehicle minus the speed of the wind or the current, whenever you're dealing with a problem like this about winds or currents. So always keep that in mind. So here we were solving for the speed of the plane, that was my x, and that's why x came first. In the other one, we were solving for the speed of the current, which is why the x came second. So it all depends as to what x represents. That's why at the beginning, I always make sure to define my variable so I know where to put it when I'm writing out those rational expressions. And that's solving rational equations using word problems.